My name is Suvrath Mahadevan. I'm a faculty member at Penn State University in the Department of Astronomy and Astrophysics. And I'm the principal investigator of the Habitable Zone Planet Finder, which is a near-infrared cross-dispersed shell instrument at the Hobby-Eberly Telescope in West Texas, as well as of the NEID instrument, which is currently being commissioned at the WIN 3.5-meter telescope. Yeah. So why do we build instruments? So I build instruments to explore and discover. I view the technology really as an extension of our curiosity. So we build to push into new regimes of precision. So in my case, my interests are exoplanet detection and characterization. So I have developed technology and built instruments in precision spectroscopy, as well as to advanced precision photometry. The personal qualities that I think are very important for instrument builders are to build a team. Instrumentation as practiced today, right now, is a very complex, multifaceted, and multidisciplinary endeavor, and it's no longer possible for a single person to do it all. And I think the other ability is to value contributions from all team members, both academic and non-academic, including our commercial team members. As well as empathy towards your team members, to understand where they are coming at it from, what their constraints are, and to help everybody get to the same point. The other thing I think is very important is intellectual honesty and the ability to learn from our mistakes, because when you're pushing the boundaries, it is inevitable that you will run into problems and make mistakes. So it's that should not be a paralyzing event, but one that you learn from for the next project and the next. So the balance of risk, of course, is a very complicated topic. I think as people who build ground-based instruments, we have a luxury that our colleagues who build space instruments don't have, which is that if something goes wrong, we usually can go in and try to fix it. It doesn't require astronauts. It doesn't require elaborate launches. We can just go back to our telescope. So this is often why key technology or new technology, or what's viewed as risky novel technology, first gets tested on the ground. And in terms of the balance of risk, I think it's risky also to not take the risk of new technology, because then you stagnate. So we have, for example, with HPF, when we started building the Habitable Zone Planet Finder, it was not obvious that near-infrared detectors would support a few meters per second radio velocity precision, and we are there now. HPF has demonstrated over multiple months 1.5 meters per second RMS, which is still a factor of a few worse than what we can do with the optical, but we've gone over the last decade from tens of meters in the infrared to a meter or two. So some of these things are well worth sometimes taking the leap if the science benefits or if the science motivates it. The other places where we've often taken risks are, for example, a collaboration with NIST, where we developed a frequency stabilized laser comb because there just were no commercial alternatives. And it turns out that project has been quite successful in the sense that we've had a continuously running frequency comb at the Hobby-Eberly telescope for a few years now. At the beginning of that project, which was an NSF-funded ATI, when we were writing that ATI, we had to be realistic and say, we don't know if we're going to get to the turnkey step, right? But we did. So some of these risks just have to be taken, otherwise the field doesn't progress. So the biggest challenges, honestly, have sometimes not been technology, but funding. So HPF needed 3 NSF grants in different years, an ATI followed by an MRI followed by an ATI for us to actually close the budget and build it. And those sort of trifectas, maybe you can do once in your career, but there's no guarantee at all that you'll be able to pull that off again. The other challenge really is, how does one maintain this instrument that one has built? Because there are no obvious funding models in the US to do this. The US also has a disconnect between funding to build an instrument and funding to do the science with the instrument. And that can sometimes be a very challenging gap to overcome. And those are, I think, challenges not unique to what we're doing, but unique across many disciplines in astronomy. But they are challenges nevertheless. a few sort of project or technology or precision lessons are where we are now. I think every factor of 2 or 3 is really a new generation of instruments and technology. In the 70s, we were able to make leaps of factors of 10 every half a decade or a decade, and we're not there now. I think now it's the slow grind, but each of those factors of 2 or 3 are actually in some senses exponential increases in our understanding and in technology. The other lesson learned, which I guess I had really not appreciated when I started building instruments, is for any project that goes 4 or 5 years, stuff will happen. People will leave. People will change jobs. Pandemics may happen during such events, as we're finding out. So it's very important, I think, to think through contingency plans. And this is really a reflection, because I'm not sure I did when I was building HPF, think through a contingency plan. Luckily, we never hit a major snag, but we could have. And design for realistic scenarios, including how does this project continue if the PI is unavailable for a month or two. So those sort of contingencies would have to be thought about. And it's, I think, incumbent on the funding agencies to think through how to support these contingencies as well. Yeah, so technologies that I think we could really use our industry partners weighing in and doing better at, that are limiting progress, are probably gratings and detectors. I would say are the top 2 in my view, of which I think the detectors are probably number 1. We certainly could use better CCDs for EPRV work. We could use better infrared detectors, certainly. There are a lot of pathologies in the infrared detectors for the levels of precision that we're going into. And I think we could benefit dramatically, I think, from developments in fiber and photonic technology. Advice I would have for students is don't be afraid to push limits in technology and in innovation. Because one thing that is very specific to our field is, and it's probably true of other fields too, but in our case, our advances in understanding the universe have come hand in hand with our ability to increase our measurement precision. And astronomy as a field is deeply interlinked and tied to the technological advancements we make as a species. So really, you should be fearless when you're doing lab experiments and trying to explore new things. Be afraid of designing experiments that violate the laws of physics, but other than that, be fearless. And I think good physical intuition is important to make progress in these, but that physical intuition also has to be developed over time. And that's basically what my advice would be, I think.